And welcome back to the Glenn Gerberg Weather and Climate Summit. We're going to move into the second presentation for the morning, and that's with Lance Rothfusz from the National Severe Storms Lab, and that is a NOAA facility. Before I introduce Lance, though, I wanted to remind everybody who are watching the live stream that tonight we'll be having a town hall meeting with the residents of Breckenridge. They'll be coming into the room here at the Doubletree Hotel to ask questions from many of the scientists that are presenting out here at the summit. So it'll be a nice interactive back and forth question and answer session. And if you have questions online again, please feel free to submit them. We'd be glad to ask them live during the town hall meeting tonight. So with that, I would like to introduce Lance Rothfusz from the National Severe Storms Lab. He's going to talk about the 2015 severe weather season and also an exciting program called Facets that Lance will tell you all about. So if you're not sure about Facets or NSSL, take a look at this short video, and we'll be right back with Lance's presentation.
New science and technology are changing the way we predict severe weather. With advanced computer models, forecasting where a tornado will touch down even an hour or two from now is no longer just science fiction. The NOAA National Severe Storms Lab hopes to capitalize on this technology with a project called Facets, short for Forecasting a Continuum of Environmental Threats. It's a complete reinvention of the watches and warnings the National Weather Service currently uses.
When the Weather Service issues a tornado warning now, it's for a very large area, and everybody in that area gets the same message. What we are doing with Facets is honing in on the area where the threat is greatest, and individuals will get their own bit of information every half mile, updated every 2 minutes, so that it becomes a personal forecast telling you exactly what your risk is at that location. So imagine you're sitting at this dot, and you now see that there is no tornado warning in effect, but your relative threat of tornadoes is starting to increase. It's still increasing as the storm approaches. It's increasing some more. Now the tornado warning is issued. And so for people who have low risk tolerance, like hospitals or schools where they need advance notice, if we can give information indicating that there's a lower risk but it's increasing before the standard warning would be issued, they can take action ahead of time and have a longer lead time to protect the people that they're serving. Another example shows where you are outside the tornado path, but you're in a tornado warning, but the path of the tornado is actually to the north of that location. So even though they were in a warning, with the Facets approach, they didn't get overwarned for an event that did not hit them.
Before Facets can go live, there's still much work to be done. Researchers are working with both forecasters and social scientists to ensure information is communicated clearly and that people know what to do. Learn more here and follow us.
Well, good morning. My name is Lance Rothfusz. I am the Deputy Director of National Severe Storms Laboratory, and as you can tell from my voice, I'm also battling a cold, so I'm going to try to persevere through that today. It's a delight to be back here. I say back here because I was at this conference 20 years ago. 20 years ago, after I had just finished the Atlanta Olympic Games, providing the weather support, leading the weather support for that. So maybe in another 20 years you'll have me back. I don't know. But it's a delight to be here. I'm actually going to be doing 3 things that I want to cover today. Here we go. 3 things that I would like to cover today are a recap of the 2015 severe weather summary, severe weather events. And then you just saw the little clip on Facets. I'd like to dig more deeply into that, explain that a little bit more. And then in the middle of that, I'd also like to talk about the things that National Severe Storms Laboratory is cooking up in the back room. Things like warn on forecast and phased array radar and these kind of things. You've probably seen some of those as well, but we've tried to put this all together as a package. So I'm going to start this with a presentation, actually doing this for Greg Carbon, who couldn't make it to this. He handed it off to me, and Well, actually, I asked him for it because Dave had asked me to come and make the presentation here on this. So I will be a pale imitation of Greg Carbon in doing this. And so if you have any objection to the 10 top weather events that have been selected, or any disputes over the data and facts and that sort of thing, my name is Greg Carbon from the Storm Prediction Center. And Greg, by the way, I don't know if you heard it, Greg has been selected to go to the Weather Prediction Center. So he's making a move out to Maryland to start a new career, new part of his job out there. So I thank Greg for sharing this information with me. Now, as luck would have it, Dave, being the slave driver he is, he'd asked for this presentation as early as possible, so I was finishing the presentation. I think I got it to you somewhere about December 19th. And if you know anything about what happened a little bit after that, say about December 23rd to 25th, we had a severe tornado outbreak that would have certainly made the top 10, but because I already had my material in the can ready to roll, I would at least like to give honorable mention to the December 23rd, 25th event. We ended up with 36 tornadoes on the day. EF4 was the strongest, 18 fatalities, all the way up through Mississippi, Tennessee, Indiana, Illinois, and Alabama. So certainly that would have made the top 10 list, but since I had to do it before Christmas and the holidays got in there, didn't have a chance to cover that. So let's start with number one. And this is actually not in a numerical order in terms of significance. I think Greg kind of put this in chronological order. So we're going to start at the beginning of the year with the Boston snowfall records that just got buried. From the January 1st to March 31st, you can see the snowfall totals. Kind of a rare thing to do an animation of snowfall in feet, unless you're out here in Colorado. But this was kind of a significant indication of the event and how the values stacked up from January 1st to March 31st, measured in feet. So out of that, you see on the order up in upstate New York, the 12 feet and such, and then in the Boston area, 9 to 12 feet. And we get a little more deeply into that. So, some good videos out of this event as well. I think you probably have seen some of these, just watching the time lapse of the video just from January 26th to 28, starting with just a smattering of snow and then rapidly accumulating to about 30 inches. Pretty impressive. Yeah, could be DC. Is that your forecast? Snowfall, total snowfall, you see again 30 to 36 inches in the Massachusetts area for that particular event, 26th to the 28th. Shattered all sorts of records. Brad Panovich and I were at a conference up in Boston where I gave a presentation as well, and I heard some amazing stories from this event. The figure in the lower right-hand corner in particular was one that I vividly remember. It's where they dumped all the snow, and then just as it melted, all the nasty stuff that they kept finding in the snow, and the chemicals, and it was a mess beyond just the snow itself. The aftermath created quite a bit of difficulties. So not only was the snow a story, it was the wicked cold. For record 43 days, the temperature didn't rise above 40 degrees in Boston. The snowiest winter on record, 110 inches. The snowiest February in Boston on record, almost 65 inches. And the most consecutive days with snowfall, 16 days consecutive snowfall in that as well. Flipping a little bit later to getting in more into the spring, January, February, March, early spring time frame. One of the things that Greg noted was a nearly watchless winter. Typically, we will have a few severe thunderstorm and tornado watches through the south especially, but in this particular year, you can see by the color coding here, the paucity of watches. For the first 3 months of the year, only 4 tornado watches and 9 severe thunderstorm watches were issued anywhere in the United States. How does that stack up? Well, this little eye chart here is a historical representation of the watches. If you start at the bottom, you see from 1970 all the way up to 2015 by month and by day. And color-coded by the number of tornado watches and severe thunderstorm watches. So you can see sort of by the brighter the color, the more tornado watches and more severe thunderstorm watches there were. Well, what you see at the very top of the chart here, see if I can get my cursor going. At the very top of the chart here is a long span of no watches. In fact, 51 days in early January, February, March without a watch. And the Storm Prediction Center folks were just sort of itching at that point, waiting for something to happen, because that's a long dry spell for them to go. Longest watch-free span in days in 29 years. So there was something significant about that. I think the upper ridge had set up nice and strong, and it made it very difficult to get anything going. Anomalous low number, as I said, January, February, March. The 51 days span in January, February for the longest in 29 years. And I think I've already covered that. Record for March, 23 days. So number 3 is it's a departure. It's a departure from the event, the severe weather event. This is actually kind of noting, Greg wanted to note, a seasonal severe weather forecast that kind of got their attention. So what you see here on the 2 charts, on the left-hand side is the El Nino climatology. Some folks out of Columbia, researchers from Columbia, Alan Tippett and others, put together this study. And on the left-hand side, you see the El Nino response by the atmosphere. And the upper chart is the geopotential height, 500 millibars. The middle chart is sort of the mean moisture. And at the very bottom is the storm relative helicity, prediction based on historical reanalysis for El Nino. On the right-hand side is the La Nina. So you can see a stark difference in terms of the parameters that go into a severe weather event, depending on an El Nino event and a La Nina event. And of course, in the December, January, February time frame from 2014 into 2015, we were dealing with a kind of a modest developing El Nino, and that would have signaled the things on the left-hand side, sort of a higher number of severe storm relative helicity and moisture and lower heights. So what they do out of this is put together just sort of a prediction, and these are really tough to do. As you saw from the Dr. Klotzbach's first presentation, these climatological or seasonal predictions are very difficult to make, especially when you're talking about severe storms and when you got severe convective type of activities. But what they did on this is, you see on the right-hand side, this chart on the right-hand side corresponds to the dashed area. They found the highest statistical significance to the dashed area. So this chart on the right-hand side corresponds to that dashed area. On the very top, the red corresponds to a warm season, an El Nino type. The black in the middle is sort of the neutral, and then at the very bottom is the La Nina. We're on a colder cycle. So where were we in that time frame, December, January, and February? We were probably somewhere right in here as the sort of on the cusp of El Nino and the neutral as we were developing. And as they had predicted, the hail and the tornado events fell right in there, about 100% of climatology, a little bit higher than that for that March, April, May time frame. Now, is this something you can run to the bank with and say, okay, because December, January, February did this? You all know the answer to that. You can't run to the bank and say, we're going to absolutely say this. But this is one of those seasonal forecasts that got the forecaster's attention, that, hey, there is a little bit of skill there. You can start to see the trends, and you can start to see the general characteristics of the season at that point. So it's just the beginning, and much more analysis and such that has to come up from that. Number 4, the April 9th, Fairdale, Illinois, EF4 tornado. I got some statistics on that here in just a bit. One of the more interesting things, Greg put this together, I thought was pretty ingenious. On the right-hand side, you see the traffic map from Google Maps on Highway 72, just outside of Fairdale. You notice that the traffic all goes red, and then it goes nothing in between. Most likely, the path of the tornado, debris on the road. So traffic stopped, couldn't get through, and all this. So I thought that was kind of an ingenious use of Google Maps to determine in real time where the path of the tornado may have been. It was a fairly classic spring condition, the warm moisture, deep low developing as it came through, and you can see by the numbers there, the 5 tornadoes that were the most significant tornadoes that were predicted out of that, or detected out of that. Probably one of the more exciting things about this is the use of ensemble storm scale forecasting. in this event. This is what you see there in the contour is the contour of maximum rotation velocity, updraft helicity, that's what it is, maximum updraft helicity tracks. And again, this is an ensemble, 7 members all merged together to try to predict where the greatest rotation is going to be. Had this verified, Chicago would have had quite an exciting day. Fortunately for Chicago it didn't, but unfortunately for Fairdale, it did indicate that there was going to be some potential for especially destructive tornadoes. The oval area was the area for the Storm Prediction Center's 10% probability of significant tornado, and you see, of course, they're going to show the great stuff, right? They nailed it. They had at least 4 tornadoes in there that were of that category. The tracks indicated there. Still, even looking at an ensemble storm scale capability, we're starting to see skills there that are getting our attention. Starting to say, hey, we've got some skill in predicting hours out in advance where that rotation potential might be the greatest. Did it nail it? Not quite, not to the liking of local forecasters, but it certainly helped. After the Fairdale event, you can see from satellite the dark line there, highlighted by the red arrows going up right through Fairdale, and then the Civil Air Patrol did a flyover a little bit later, and you can still see the black earth just scoured out from that tornado as it went through. The Storm Prediction Center felt that they hit this one pretty well. I think anybody would say that they hit this one pretty well in terms of 6 days out, identifying the potential, the high potential for severe weather, and then as it got in, you can see 6, 5, 4, 3, 2, 1, and into the event. They kept pretty stable on it, so their guidance and their forecasters were right on the money with it. And you see some of the statistics there. Unfortunately, 2 deaths and 22 injuries with a 30-mile track for that one particular tornado. All right, number 5. This one was a little close and personal to me because of the rainfall in Oklahoma and such. The wettest month on record for the continental United States. And that, looking at the climate divisions and standardized anomalies for that 1950-2007, you see in southeastern Oklahoma there, we were pushing 4 to 5% anomaly on the rainfall in that time frame. Here's the accumulated precip as you watch from just the month of May. And you see it just keeps on piling up in the 12 to 18 inches, even to 24 inches. I ended up with 18 inches at my house in the month of May. I had just built a new retaining wall, and I was a little nervous standing outside watching it. It withstood it, so I figured if it withstands that, I'm good, I hope, for the future. But local areas in Oklahoma up to 24 inches in some cases too, so quite significant all in one month. And then into the January to May time frame, the all-time wettest 70 to 90 years in the 70 to 90 years records we've had. So all of us in the central United States, southern plains, while we squawk about the drought and all that, nobody's complaining. I heard 0 complaints about the amount of rain that we had. Now, that's not to say we didn't have to deal with some flooding issues and that sort of thing, but a lot of the basins and things that were drying up were empty, got filled up with this rain. You see this on May 6th in particular, 7+ inches of rain. What this chart shows is sort of a accumulation of precip for given years. The light green lines are for a specific given year. We've got 2015 highlighted here, and you see that May 6th event, 7+ inches, just jumped up and then ended up in the 99th percentile for events in that time frame, and then finished the year at 28.7 inches. That May day, this is really kind of hard to believe, knowing how weather is in Oklahoma. To get 7 inches is still the 3rd heaviest of all time. I thought that would have been maybe more events than that. I don't know how many of you have ever driven over the Red River in the upper right-hand corner between Texas and Oklahoma, and that's a big drop-off, way down. You notice the river. This is on the right-hand side. There was a great deal of concern of whether the bridge would even withstand the force of the water going through there. Fortunately, it did, and we have a lot of stories to tell for it. But several other events. Actually, was a real minor tornado that actually occurred, hit the Norman Hotel there as well. So all the local weather geeks got their excitement with that particular event. So again, number 5 is the wettest month on record. I think that says it all right there. I was going to flip to the other side. So as wet as the central United States was, the western United States was dealing with a considerable drought and heat event. It's sort of a continuation of previous years. That January to September timeframe was set some of the records for the 4th and 5th driest timeframes on record. You can see the record warmest 121 days in that time frame where it set records. Well, along with the high temperatures in the west, there's another thing that goes along with it. It's the fire. So it sort of combined these two. 6 and 7 are both the heat and the fire. You start looking at the January, July, and August temperature anomalies, and you see 13 was not great. 13 was certainly warm. 14 got worse. 15 made it even worse. So with all that drying going on, certainly the Northwest and West paid the price with the the fire. You also see from the California average temperature, just averaging all the temperatures in California over the years, certainly the trend line is up, but especially from 2010 or 11 in the past 3 years, that spike that has occurred harkens of the movie the Inconvenient Truth, when Al Gore gets on his cherry picker to go up and shows the temperature at the end of the year. Really kind of interesting and significant that last couple of years has really spiked up. So with that drought occurring, you see the expansion of it going into 2015. The chart on the right, I think, is fairly profound. We're getting a lot of rain out in that area right now, which is good, but you really stand back and look at it, it's still not going to be enough. In order to get back to climatology, and in order to get back to normal in that area, the chart on the right shows how much rainfall they're going to need. I think the 300% down in Southern California is on the order of about 33 inches of rain that they're going to have to get in the year, and that's off the chart. So despite all the rain and the basins and the reservoirs being replenished, they still have a long way to go with the amounts that they got there. The western megafires. The chart here shows the size of the pie chart shows the number of fires that occurred, and then the slices of the pie indicate which years they occurred in. And you can see Washington in particular in 2015 had more what they call mega fires, 10,000 acres or larger in that time frame than in earlier parts of the year. Idaho wins the prize as having the most amount of mega fires in that whole time frame of 2011 to 2015. So it's no surprise that with the drought and the heat, the fires start to come off of that. You got an animation there in the upper left-hand corner that shows the number of large fires that NIFC had seen over that time period. I really like the panorama shot down the bottom. This is a shot of Yosemite, but it's in sort of panoramic, but by year, from 2011 to 2015. So you look at the snowfall, snow accumulation on the left. It's quite heavy, quite good snowpack, but as you get farther into closer to 2015, that snowpack is gone, which portends a troublesome fire season for the next year.
What month was that?
That's a good question. I'll have to go back and look at he's got his notes buried in here. I don't have that one memorized. So 6 and 7 were the combined heat and drought in the warmest year on record in the western United States, and as Dave just announced, for 2015, the whole country is going to be setting records. That's going to be another story for 2015 as well. In number 8, it was in southern Utah, a deadly flash flood event. It's sort of like the worst possible scenario where you had antecedent conditions, pre-existing conditions of wet soil, and then a couple of storm systems that just sort of set up shop right over this one basin. In this case, total of 19 fatalities. 7 adult explorers were killed in the Zion National Park. 12 others were killed when they drove their car through water. So this is the thing that we ask the media to help us get that message across. I know you're doing that. Keep it going. It's just people still don't think it's going to happen to them. On the right-hand side of this chart, you will see the basins and where the fatalities occurred. It's really, like I said, sort of a perfect storm for flash flooding because it's the mouth of 4 different canyons that comes right into that location in Zion National Park. And as I said, the August 2015 rainfall was well above normal, pushing 200% of normal already, and then to have a couple of major systems kind of set up and a little shortwave trough that set up in the west coast and kept pushing moisture out of the Pacific. Their precip anomalies, precipitable water, was pushing the 90th percentile in that time frame. So not only was the surface moist, but the atmosphere was moist as well, and put those together in a basin that's already prone to flooding, and you can just see what happened here. Some examples of the estimated rainfall in that area, pushing 2 inches, 2 to 2.5 inches for a couple of locations in there, right in that basin area. I don't know about the rest of you. When I saw this image on the right-hand side at the bottom, I was a little disturbed. There's got to be a story to this one. I don't know if anybody knows that story, but I don't know about you, but after there are fatalities and cars driving off roads and there's muck and mud and stuff down there, I would really not send my kids down into that area to take a look at. So there's a interesting side story on that one. People, curiosity seekers, going out and taking a look and putting themselves at risk as well. So number 8 on the list was the 20 fatalities. I said 19. It's actually 20 fatalities. Interestingly, that was actually 2 times the number of tornado fatalities in 2015. And what gets the attention? It's the tornado fatalities and such. Well, no, I take that back. Not counting the December 23rd, 24th. Right, that probably changes that number. Is that where you're going, Bob? Okay, yeah. Thanks for keeping me honest on that. Oh, and interestingly, Zion National Park is now reconsidering their permitting rules for people coming in. Well, unfortunately, sometimes it takes something like that to get people's attention, and hopefully they will do that. So number 9 is Joaquin in South Carolina rain. For those of you in South Carolina and on the East Coast will remember this all too well. It's sort of as Greg so cleverly calls this, the coalescence of chaotic coincidence, which is just the atmosphere. We had a deep low developing in the southeastern United States, a sort of a decaying front off the coast, and then Joaquin sitting out there and spinning like crazy, shoving that moisture to the east. Greg points out here that the wave heights were also a big story out there. In a 12-hour period, they tripled in height, went from 6 feet to 18 feet up in the New Jersey area. So it wasn't confined to the South Carolina area, all up and down the eastern seaboard. There were significant impacts. He says other things are moving around too, not just the fronts and the moisture and all, but also the forecast of Joaquin, whether it came from European Center and all the other ensembles. I'm biased on this. This is what I would prefer to see the ensemble output look like from Tropical Prediction Center, because you see the bimodal and the differences in the paths rather than one trumpet kind of thing that shows, or a megaphone thing that shows sort of a historical background to it. So the models were all over the map and making it a very difficult forecast for those along the East Coast to try to figure out if they were going to have more of a significant event than they had already. So the final tally of that was Joaquin, if my recollection is right, really didn't impact the land at all, other than throwing the moisture back over into along the coast and the wave pattern. So you see here sort of a loop from October 1st to 5th of the moisture, the rain from the radar, the big picture, if you will. And you just see that it keeps on coming, just streams training right over that same area in central and eastern South Carolina. And the total estimated rainfall totals, again in this one pushing 20 to 24 inches, and certainly a lot of flooding events. You can see on the lower left-hand corner the number of roads that were closed in red and the number of bridges that were impacted in blue, and mostly in the central part of the state. You see on the right-hand side sort of a satellite image as well of the rain before and after the event. On the left-hand image is the before, and on the right-hand side is, you can just see the water pooling everywhere in there. So it was a combination, I hate to say perfect storm is overused, but tropics and jet and topography, all that put together, plus produced a 1,000-year rainfall event, 21 fatalities, unfortunately. And then, not surprisingly, hundreds of dam failures and major roads damage during that event. And the number 10 on his list was the High Plains tornado in November. Really, we do get those kind of events, but to have them at this level in terms of rating, EF rating, was fairly significant for us. So in Kansas, Nebraska, and Oklahoma and Texas panhandles, this was the biggest November tornado outbreak on record. I think you got an animation here. It doesn't look all that spectacular on the radar loops, but just because of the shear in the environment at the time, everything out in that Texas, Oklahoma panhandle area, western Kansas, all those little blobs were spinning like mad. And it was just an incredible sort of event because of the shear profile it set up. You know, the atmosphere really doesn't care what time of the year it is, right? It's going to be, if all the ingredients are there, you're going to have to pay attention to it, and indeed they did. The Weather Service blanketed lots of tornado warnings and covered it quite well. Preliminary count for this event was 35 tornadoes, 3 of them the EF3 tornadoes. One was the 50-mile-long tornado track in southwest Kansas. And again, for November tornadoes, we just don't usually use those phrases, but this was an anomalous year. And where you see normally the tornadoes, and this is sort of the climatological mapping, the focus of that tends to be in the southern United States, and now we've added many more up in the, several more up in the western parts of the United States. And you know, these are some of the more dramatic ones. You just think about this with the moisture and the lifted condensation level being so low. The storm tops were not that high. Some of these images were quite spectacular, even almost damaging wall clouds as they formed. Some of the pictures from them. So undoubtedly embedded somewhere in that wall cloud in the upper left is a tornado, but the wall cloud itself penetrated almost to the surface. And there you have it. Number 10 was the High Plains tornado in November. And a key point on this one was that the storms occurred through the night in Oklahoma, and so that makes it a more challenging event for that part of the country, or any part of the country, to have at nighttime. All right, so let's give Greg a hand for his excellent presentation. So now I can move on to the stuff that I know a little bit more about, the stuff that the material I put together. And this is a little bit on NSSL's coming attraction. Some of the things that you've probably heard about, some of the near-term things. In fact, MPING, meteorological precipitation indicated near the ground, got to have an acronym, is already out there. There's a little bit of a buzz going on in terms of licensing and all that. We're trying to get all that straightened out, but our intention through all of MPING is to get the data out there for the public to use, especially the Weather Service offices to use, and for you to use as well in determining snowfall and precipitation type. I'm going to go into a little bit more here in a minute. MRMS, multi-radar, multi-sensor system is already going operational with the National Weather Service. I'll describe that. I'm going to talk about something called mirrors, and then facets at the very end. And then long-term, way over the horizon, things called Warn on Forecast and the phased array radar. So let's talk a little bit about MPING. This really began as an experiment. We had 4 researchers that wanted some ground truth. And in a happenstance conversation in the hallway one day, one of the researchers happened to talk with somebody who had actually developed a phone app and said, hey, it sure would be nice to have a phone app that people could do crowdsourcing and collect the precip type, and next thing you know, about 2 weeks later, he comes up here, how does this look? These kids are phenomenal when they start set their mind to it. Well, what we're trying to do with MPing, and one things that MPing helps us do, is to help calibrate the radar algorithms. That was really what it was designed for. If we knew the precip type, exactly where it was, and the hail size, and these kinds of things, we could calibrate the radar algorithms as they were being developed. And that's about the time when I came to the National Severe Storms Lab. I had spent 25 years with the National Weather Service. I jumped the fence to the research side, and I immediately saw the value, I think we all would, of seeing the value of crowdsourcing precip type and hail size. And so we made a concerted effort to get it into the National Weather Service offices, and then also get it out in a sort of a public stream that you would all be able to access and get your hands on. So right now, AWIPS 2 is the target for the National Weather Service, and we do have the MPing data flowing into AWIPS 2. The forecasters are seeing the data. We would greatly welcome your assistance in getting people pointed to the MPing app and getting reports, because that information comes back to you as well. And I don't know, should have tried this ahead of time. Do I have internet access here? Okay. So if you haven't seen the MPing data, well, let's get a background map here. Of course, this is going to do this. Oh, they're very difficult to see. The background map is really dim on this. But here's Florida down here. Just use your imagination, continental United States. So you see animations of the precip type and such, and that's, again, when you're in the warning environment or trying to predict what's happening out there in real time, you couldn't ask for more in terms of detailed analysis. And the folks, the crowdsourcing, the people who are out there doing it, one of the complaints we often get about it is, well, can you really trust them? Can you trust the reports? And our experience has shown that crowdsourcing usually takes care of itself. One of the analogies I give is when you're working severe weather in the National Weather Service office, you get those phone calls when somebody says, well, I got softball-size hail. Nobody else has softball-size hail. The radar doesn't support it. So you get those anomalous reports that just stand out, and you kind of go, I don't really believe that. And on MPing side, if somebody does that, it really stands out, and the forecasters are able to say, they're used to that, right? They're used to misinformation and dealing with misinformation in a warning environment. So by and large, the data have been really credible and believable when they come in, and this worry about, can we trust the data is really not well founded. Multi-radar, multi-sensor system. This is like the drink from the fire hose. Here we go. If you take all the data that we collect in the National Weather Service, and you take radar data, and then you combine it with other radar data, surface observations, satellite observations, lightning data, precip amounts, different types of radar, and put it into one package, one 4-dimensional domain. This is what MRMS is. And I'll give an example of that. Multiple radars provide one answer, each from their own radar, right? You get one radar, it slices at different elevation heights, but if you got 3 radars looking at the same storm, you can merge them together and get much more detail about that storm. And this is what the power and the strength of MRMS, not just for severe storms, but also for rainfall amounts. So the QPF forecasting and such that has come out of MRMS has been quite spectacular. So a single radar, we all know about the cone of silence. In this particular case, you see a storm has come over the top of the radar, and you lose the information over the top. It really didn't happen this way, but just the fact that storm went over the top of the radar, you lose the radar analysis. So what would happen if you were to multiply or to combine it with additional radars and neighboring radars? And what you see here is filling in a lot of the gaps in the cone of silence, and you get a much better mapping of the precip amounts. And if you're looking at vertically integrated liquid, prior to the event, without on a single radar, you would see, oh, it's coming up, I'm going to issue my warning right here. But by having multi-radar capabilities, that gives you that vertically integrated liquid value much sooner. In this case, about 83 minutes before that single radar did. So we are seeing tremendous improvements in the severe convective warnings because of MRMS and what the Weather Service has been using that. Now, imagine this. If you can take all your data and put it in a four-dimensional domain, a cube that moves in time, if you've got it in a digital cube, you can start doing some really cool mathematical analyses of this. And this is what the strength of MRMS is. Many of you have seen these hail swaths and the things that come out of this. This is coming out of the MRMS collection of radar information, satellite, and such. And we get a lot of questions all the time. Is there any way you can tell where the hail swath was? Well, now with MRMS, we have much higher confidence in the hail swaths, and that's turning out to be a boon for the private sector to give a much better idea where those paths went, where those hail paths went. Not only do you get hail accumulation or hail size predictions, you also get rotation tracks. You start putting it in a cube like that, you can see where the rotation is strongest. And again, the FEMA is actually using these rotation tracks in terms of getting some lead on where they might need to start sending resources to be ready for responding to tornado touchdowns and that sort of thing. So we're already paying dividends for the country in what MRMS does.
Just real quickly.
Yes?
Data go to a central location, how is it?
It goes to a central location. It had been coming to NSSL. We have just now offloaded it to the National Weather Service, so they have taken ownership of the data. And we're still working through how we get the data out through NOAA Port and others. There's probably going to be a subset of the data because it's just so voluminous. But we just went active on it like 6 months ago, and we've got some additional upgrades and things that we want to do. They're going to be running it at the College Park facility, and then have a backup facility in Boulder, Colorado, so we have redundancy in the system if the system goes down in any way. Hearing some really good things about it from forecasters, and I think Jennifer was also mentioning the flash. I'm not going to talk about flash here, but sort of the hydrologic part and what the flash flooding capabilities are for mirrors as well. So I think some of you have already seen the benefits and the results of that. I want to talk a little bit about mirrors, and I jokingly call this great idea, worst acronym ever. Multi-year reanalysis of remotely sensed storms. And basically what we're doing with mirrors, we're taking 15 years of level 2 radar data and doing a reanalysis of it, along with environmental data. And what this is going to be telling us, and we're seeing the results, and already preliminary results, the researchers are not quite believing it because it's that good. But what this does is it says this type of storm in this type of environment typically does this. It turns right, turns left, it produces baseball hail, it dies, it produces tornado. You take your pick. You can develop a statistical analysis or prediction of what that storm is going to do. Now, I, as an old weather forecaster sitting and looking at the radar, all you have is detection, right? And you got to make inferences about what that storm, trends, and all that. But to have a predictive capability while you're sitting there at the radar, knowing of this type of storm, this type of environment might do certain things, tremendous advantage to the operational forecaster. So that's our hope right now. I call it real-time storm scale MOS, model output statistics. It's real-time, it's sitting there while the storm is going on. It runs very rapidly. While the storm is going on, you get sort of an analysis and a predictive scheme for what that storm or those storms might do. We will be testing that in the hazardous weather test bed this coming spring. And while I'm on the subject of hazardous weather test bed this coming spring, we are opening the doors. Last year we opened the doors to emergency managers to come in and sit in while the forecasters are developing some of the new facets type data and giving it to the giving it to the emergency managers and getting their opinion of it. We want to open the door this year to the broadcast community. So if any of you are interested in coming to Norman for a period of time and sitting in there and helping us guide the development of some of the tools that go into facets and facets itself, come talk to me afterwards. I'd be glad to entertain that discussion. All right, so I'm going to shoot across the horizon here, way over the horizon, not too far, maybe 2025 time frame. Warn on forecast. I think we all understand the concepts of forecast versus detection. Well, the way we issue warnings right now, it's basically warn on detection. What warn on forecast is a an ensemble of storm scale concepts or numerical values. In this case, this is probably one of the early successes we had with it. April 27th, 2011, a 36 model ensemble forecast probability of storm rotation compared to the tornado track. So across the bottom, you see the predictive contours for rotation well out in advance, 135 minutes before the tornadoes touch down. So basically 2 hours in advance. And you see the two paths of the tornadoes there on the far left-hand side at 21Z. This was, I just chuckle at this sometimes because the researchers are looking at that and they say, not quite. We got to get it better. We got to get it tighter. I'm thinking 2 hours in advance to be that close compared to what we're doing now, sold, right? So they're still tinkering with it and doing better on it. So as you move from left to right, even on the far right-hand side, a 90-minute forecast of the tornado just nailed it. Now, I want to stress on this. Warn on Forecast is not just tornado prediction. We emphasize that it is all severe convective prediction. And Nusrat Youssef and others have been putting out papers just recently on the precipitation forecasting side of Ensemble, and we're seeing some really stunning results with flash flooding prediction from the Warn on Forecast ensembles. All right, another thing across the horizon, and the reason I'm doing it in this order before I get to facets, because this facets ties all this together, is the phased array radar. Eventually, these WSR-88D radars we have out there are going to give up the ghost. Right now, we're working with a Spy 1 prototype that we got from the military, and that number 1 is significant because it was built back in 1970-ish, and it was the first one, and then it was a hand-me-down they gave to us. But we transformed it to be a weather radar to test the concepts. And here's what you're seeing in terms of some of the capabilities from that phased array radar. The rapid update speed, the 1.2-minute updates versus the current 4.2-minute updates that you're seeing on the standard radar. One of the best descriptions of this that I ever heard was, it's sort of like watching a football game. With the existing radar, you turn your TV on every 5 minutes and turn it off. And you go back, turn it on 5 minutes later and turn it off. Really hard to tell what's going on in between, but with phased array, we have the TV turn on more frequently than that. And what's important about this for the meteorologist is to understand that we are now starting to see the thunderstorms as a process, not a thing. I think forecasters tend to think of a thunderstorm as a thing, and it's not. And with phased array radar, now you can see the evolution of the updraft, the downdraft, the cores, the outflow, all these things starting to show up. So you start to see the evolution of the process. And that makes a huge difference in how the forecasters are thinking. We understand now with some of the training and things that we're going to have to put together, we will have to train them on that. Well, that's phased array radar. We put the M in front of phased array radar for the multifunction. The idea here is that we actually use it not just for weather, but we actually use it for other phenomena as well, or other things out there as well, like aircraft, or I love what they call it, non-cooperative targets. In other words, missiles and things coming in for that Homeland Security and the military would be very interested in. If we go with this conventional strategy where we just sweep everything all the way around, we're sweeping a lot of empty space, right? What phased array MPAR does, it targets things. Once it sees it, it tracks it, all right? And you track only the thing that is of interest to us, and the clear air does not get sampled. I take that with one caveat. We do a clear air sample once in a while, but it's just to see if anything new is cropped up on the screen. All right, it's much more efficient in radar operations, and also opens up the door to reducing the number of radars that we have across the United States. Right now, I forget the exact number, it's on the order of 1,200 or so radars between FAA, military, and the National Weather Service. There's something like 1,200 radars. If we were to take this in multifunction and use it for multiple purposes, we could take us down to about a half or 2/3 of that number. So significant cost savings to the public. All right, finally, how am I doing on time, by the way? What does that mean? 20 minutes. All right. Plenty or 20? Okay. Okay. So let's talk about facets. How many of you seen the facets presentation? Some of you have. All right. Not really. So, okay. I've done this so many times. I think everybody has heard facets and has heard it all or seen it all and all that. So let me start it this way. Those of you who have seen this already, don't play along. This is my little game at the very beginning here. Is there anything wrong with this tornado warning? I'll let you look at that for a moment.
Not very visual.
But that's the way we do it.
Sorry.
But
You will.
all right. But this is the way we do it.
Doesn't talk about cities in the map.
Sometimes we do that. But we don't have to. It actually does say northeast of Cleveland is moving toward northeast. All caps. Nice try. That's the way we do it. We love to shout at people, right? All right. So I'm not going to string you along any longer. Huh? Sometimes we do it this way. All right. So this is a trick question. This is a trick question to make a point. All right. Unless you are OCD, if you could put it back up on the screen. Unless you're OCD, you would know that Sunday did not occur on February 21st in 2014. Now, I didn't expect anybody to get that. That's not the point. The point of this is that warning was actually issued in 1971. How many of you were born before 1971? We have members of the audience that weren't even born yet. Oh. So my point here in showing this is that we have not changed our warning paradigm for over 40 years, even 50 years. We're doing it the same way we did it back when we had things like these. You remember these things? I really like the popular science part too, that phone. The take-along phone, the brick. It's the take-along telephone. It's going to be big, back in 40 years ago. It won't catch on. It will never catch on. So the point here is that a lot of things have changed in over 40 years, yet the National Weather Service continues to do this same methodology for issuing the warning. So we took a look at it from National Severe Storms Laboratory side and said, maybe we need to come up with a new approach. Now, I want to qualify everything I'm about to say as this is proposed. The National Weather Service has not signed off on the line, this is what we're going to do. They're looking at it, they're working with us, we're exploring together, right? So I don't want anybody running out and saying, Weather Service is going to do this in 3, 5, 8 years, whatever it takes. But we're looking at it, and we're hoping that we come about to that. But this is a part of the research and development that we're in right now. In the current warning system, we have this time-space continuum, left to right. The event is what matters. Right? This is the event that impacts people. And that event, it's not just tornadoes, although you hear me use that as examples throughout this. It's not just tornadoes, it's also hail, winter weather, fire weather, aviation, tropical. It can be any event that is occurring, flooding, anything that's happening at a given time. There is this time-space continuum leading up to it that's very important. And we all know how this works. In that time-space continuum ahead of time, we get the outlooks from Storm Prediction Center and WPC, and those outlooks tell us something. As we get closer to the event, we start issuing the watches, and then we get into the event, the warnings start. We all know the routine here. But this is a very product-centric and deterministic or binary approach to this. I also call it presumptuous. And nobody's ever thrown anything at me for saying that. None of the forecasters have ever thrown anything at me for saying this. The act of issuing a warning is a presumptuous act because it presumes that the forecaster actually knows what the end users are all needing in terms of information. We have sort of an average use out there, but there are some users that need to have the information well in advance of when the forecaster decides to issue that warning, to pull the trigger on it, right? So that act of issuing a warning is a presumptuous act. It presumes that I know what your needs are. And that's really not fair to you, and it's not fair to the warning forecaster, right? So we have to look at this in a different light, what we were trying to do. There's also gaps. Because we're product-centric, you all know especially how this works. The warning comes out, and then you sit, and you wait for the next product to be issued, for the update to be issued. So there are these gaps in between those products, and those gaps are important. There's information voids in between those gaps. On your user side, on the receiver side, you're going, tell me something. Even if nothing has changed, tell me something that I know what I can tell to my viewers or my listeners and that sort of thing. On the weather forecast office side, we're sitting there going, well, that is starting to change a little bit, but I'm going to wait another 30 minutes for my next product or next hour for my next product. There's information needed in those information voids, and there's information to be given in those information voids. And because we're in this product-centric mode, we get ourselves kind of stuck in that. Warning polygons are messy, the current warning system. And this is one example. I'm not picking on the folks in Texas. This is just one of many types of examples where these warnings are coming out. What you see here, I just wonder about the poor folks in Sebastian, Texas, what they're really thinking is going on. They are in or out of about 4 different warnings, 3 of them severe thunderstorm warnings, 1 being a tornado warning. How do you communicate that in your business to them? It's very difficult. The warning is here, but now it's not, and all this. So warning polygons get very messy. They are also deterministic, right? Meaning binary. You're either in a warning or you're not. It's black and white. You're either in a warning or you're not. The inherently binary nature of these warnings makes it very difficult as well to communicate trends and how things are changing, which is a lot of what you do in between in those information voids when you're on air. We also have a large false alarm area. I have to explain this chart a little bit. Some people get confused, but in red, what we did was we added up the area. We accumulated all the area for tornado warnings in a given year. This is actually a 4-year average, but we added them all, a 5-year average. We added them all up. This is the 5-year average for tornado warning area. Now, for some folks, sometimes they get confused. You say, you're only issuing warnings on the eastern side of the United States? No, that's not what I'm saying here. This is actually sort of normalized to the United States, so we give you an idea of the size of it compared to the rest of the United States. The area actually issued, or tornado warnings actually issued, is in red. The area actually impacted by tornadoes is that little yellow dot. Nashville. We picked Nashville just for fun. All right? So what this is telling us is that we have this high false alarm rate when we issue our polygons for the area actually impacted by tornadoes. Question in the back. Yes?
Is this just for tornadoes?
This is just for tornadoes, yes. So so we've got to be a little bit careful in the interpretation of this, because it also, this is actually the area impacted by tornadoes in the tornado path. There are a lot of people think that, well, if it was within 5 miles of me, I was impacted, right? So the area actually where people felt they were impacted, that yellow area would probably be maybe double or triple the size, but it's still, comparative to the area that we issue warnings for, it's small. So what that breeds in society is complacency. People, another tornado warning, and I didn't get hit last time, I'm not going to pay attention this time, and this may be the one time you needed to pay attention, right? So I think we all live that in our current life. So the current warning system has its inherent problems. So what we did at NANA, yes? Yes?
You need a microphone. It is that important if you're saying it.
Jennifer Huckavina from Paducah, Kentucky. Just quick on the polygon, is there any restriction on how small that polygon can be?
No.
Just have 4 points?
Yeah.
Okay.
Yeah.
I'm asking for the flash flooding
I understand.
side of things, but I just
Yeah,
wondered
there's no
that.
minimum size. I mean, the flash flood is down a river basin.
Okay.
Yeah, we could follow a river, stream, or a creek. We could follow that.
Okay.
We could do that. Typically, we don't. We tend to err on the size of larger just to cover all possibilities.
Okay.
So, National Severe Storms Laboratory, we started looking around and said, maybe it's time. We've been doing it this way for 40, 50 years. Maybe it's time to look at a new way. So this paradigm shift, we wanted to do 3 things with this new approach. First of all, don't throw out the good stuff we're doing now. There are some things with the existing system that work. So first, do no harm. Keep the good things that are in place now. The challenges that we have, the things I just covered now, revise and reinvent those, and then look at where the science is going. Where is technology going? Try to anticipate that as best we can, the science, the tools, and society, and build that all into future warning paradigm. Now, I'm going to show you a video is actually a longer version of what you saw during the break. So this is hopefully in one fell swoop going to explain the whole thing, and I'll be done. No, I've got a couple more follow-up here. We have audio.
New science and technology are changing the way weather is predicted. Computer models can indicate the probability of all types of weather. No longer is it just science fiction to predict where dangerous weather may form hours from now. FACETS, short for Forecasting a Continuum of Environmental Threats, is designed to capitalize on this new technology and make the most of it.
When the Weather Service issues a tornado warning now, it's for a very large area, and everybody in that area gets the same message. What we are doing with FACETS is honing in on the area where the threat is greatest, and individuals will get their own bit of information every half mile, updated every 2 minutes, so that it becomes a personal forecast telling you exactly what your risk is at that location.
The FACETS information process actually begins days in advance. Long-range outlooks issued by NOAA's National Forecast Centers highlight areas where high-impact weather is possible. As days go by, the outlook locations are fine-tuned to target the location and timing of potential threats. As a high-impact weather event begins, the details of where the impacts will most likely be are displayed with greater and greater precision, giving users a better idea of what safety actions, if any, they need to take.
So imagine you're sitting at this dot, and you now see that there is no tornado warning in effect, but your relative threat of tornadoes is starting to increase. It's still increasing as the storm approaches. It's increasing some more. Now the tornado warning is issued. And so for people who have low risk tolerance, like hospitals or schools where they need advance notice, if we can give information indicating that there's a lower risk but it's increasing before the standard warning would be issued, they can take action ahead of time and have a longer lead time to protect the people that they're serving.
We don't want our families out trying to get to schools in a complete gridlock with traffic and storms coming through. Talk about a dangerous, dangerous situation. And so if parents have the ability to check out their kids and do it in a timely manner, that would be most helpful.
Another example shows where you are outside the tornado path, but you're in a tornado warning. But the path of the tornado is actually to the north of that location. So even though they were in a warning, with the FACETS approach, they didn't get overwarned for an event that did not hit them.
It'll keep us from moving the critically ill patients when we don't need to. We'll have that direct information where the storm's going, when it's going to be there, and we can keep our patients right where they need to be.
While FACETS offers many benefits, it also poses some challenges. First, the forecaster must be equipped to use the new technology.
FACETS brings with it the ability to speak in terms of probabilities, and forecasters know that there's a probability of many different hazards occurring with a thunderstorm. This will offer them a means to communicate that threat sooner and more efficiently.
The forecaster can now convey a little bit of a risk. It's increasing and increasing, and that takes the pressure off the forecaster, but it also conveys more information to the end user, even before the warning is issued.
Another big challenge is understanding how people's behavior will change based on this new information.
We need social behavioral scientists to help us understand how the information could be useful, how it could be transmitted, assure that access and comprehensibility are there, and bring that knowledge to the people who are creating the technology so that together, through time, we can make a tool that really serves the public and bolsters our collective resilience.
The FACETS project represents a fundamental change in the way watches and warnings are done for the country.
And as such, it's going to take quite a bit of research and exploration and experimentation to do it right.
As long as we can assure the information is receivable, is understandable, I really do think that the greatest potential beneficiary of this information is the public and the many businesses, hospitals, and schools that have very particular needs from weather information. This will be terrifically empowering.
To learn more about this research project, visit nssl.noaa.gov.
All right, so there you have my commercial, long commercial for facets. I hope you get the sort of the picture of how things, what we're looking at here. So facets is this continuum of environmental threats. Again, not focused on tornadoes, but any type of tornado or any type of severe weather events. So we developed this framework, if you will. From on the bottom, you see these 7 icons from left to right. That should look very familiar to you as sort of the forecast process. You start on the far left-hand side with how you do it, right? Right now, we do it with polygons. We do it in a deterministic fashion. That's how you do your warnings. The next step is that the forecaster looks at observations and guidance and makes decisions on what's going on, and then that forecaster makes a decision, uses their tools to take it from their head into the tools they have. And those tools send the information out the door as usable output, and then hopefully we get an effective response from people, and we go back and verify at the end. That should look very familiar. That's the warning and forecast process that we all follow. The difference with facets, however, is the starting point is different. It is this grid-based threat probabilities. You saw the little video animation. So every half mile or so, there's a grid point, and there's probabilities at every grid point, and they're different from grid point to grid point in all likelihood. All right, so we start differently and moving from our deterministic. So if we're going to start differently, there's going to be a ripple effect all the way downstream. Everything else is going to have to change in order to accommodate that new grid-based forecasting approach. So we knew going into this is going to have to be a modernization of the entire warning and forecast system. This is going to be a heavy lift. Louis Uccellini said it himself. This is going to be a heavy lift. It's going to take many years to do. But we're seeing some of the early manifestations of this in the hazardous weather test bed that are particularly exciting. As I mentioned, we've had emergency managers in now looking at the output from facets data and saying, yeah, this is where you needed to go 20 years ago. This is the kind of information, filling in those information voids, giving me updating information more rapidly than you would with your product-centric approach. Now, let me do a couple caveats here. First of all, we have gotten society conditioned to warnings, right? So I am not at all advocating we're going to get rid of warnings. There's going to be some legacy warnings that are still going to be there, and I think I'm going to cover that in a slide here in a moment. The other thing is I am not at all suggesting that we're going to put out probabilities to my mother-in-law, right? That she would understand what a 32% chance of a tornado in the next 20 minutes would really mean for her. We have ways, we all do it, you all do it especially well, we have ways of communicating probabilistic information in a non-numeric way. We use our words, we use colors, we use other ways to describe what is really a probabilistic forecast. So with those caveats in mind, I hope you can understand where we're going with this. So if we change the starting point, we move from this binary polygons to what we call phi, probabilistic hazard information. Every half mile, updated every 2 minutes is our target. Probabilities updating every 2 minutes and such to match the radar and ultimately, eventually, warn on forecast type guidance. Grid-based threat probabilities. The legacy warnings can fall out of those probabilities. We just have to pick what threshold that tornado warning or flash flood warning, what probability we would pick. Now that's going to be a point of scholarly debate about what that threshold should be, and I don't want it to be just a bunch of meteorologists. It's going to have to go to human factors people, psychologists, sociologists, people who understand how people think better than the meteorologists do. So we are bringing in social and behavioral sciences into this as well. But keep in mind that the legacy products are still going to be there. But it opens the door for new products, and I realize I'm contradicting myself when I said products earlier, but we open the door for a continuous flow of information with new products, like a proximity alert that we don't do right now. It's either you're going to watch and then boom, there's the warning. Now I may do significant weather alerts and that sort of thing, but not necessarily the case. And again, I've mentioned this several times, not just for tornadoes, it's for multiple types of phenomena. Yes?
From WTAJ. Can you go back to that last slide? The one thing that makes me a little bit nervous is we have tornado probability. you're not going to actually put numbers to that, correct? You're going,
Right.
Okay.
Well, for the sophisticated users, yes, the emergency managers have said they would like to see the probabilities. And our social scientists, Susan Jocelyn, a noted social scientist, has said, put the probabilities out there. There are people who know what they mean.
There are some, but you tell someone there's a 30% chance
yeah.
of rain and it rains, you were wrong.
Right, which is why I say, we need to be able to communicate this in a different way. The numbers will be in there, but you still have to communicate in a non-numeric way that people will understand. And we're working on that. We're exploring. Again, I'd love to have some broadcasters with us in the hazardous weather test bed to start exploring that. What language might you use and how we might communicate that. So yes, we get that. I'm not at all advocating giving numbers to the general public, because it's going to be hard for them to understand.
How would you restrict that from the general public, though? Because they can find anything where your social meteorologists are putting that data out there.
Yes, yeah. So here's what I suspect will happen. Here's what I suspect will happen. We will have some threshold at which the colors change, right? We go from red to yellow to green, or green, yellow, orange, red. Hazard simplification that the Weather Service is already looking at fits into this. That's what they're talking about doing. Different language, more than just the binary off-on kind of thing that you start elevating. And there should be probabilities attached to those colors. So yes, they might see the numbers, but they're going to be hopefully more fixated on what color scheme, what are we trending to? Is it going up or is it coming down? These are important things in everybody's decision making to figure out. So we understand that there are challenges, but there are places already doing this sort of thing. The winter weather, you all folks on the east side, United States, they're doing these winter weather probabilistic fields. We're already starting with the probabilities and giving them. So yeah, the concern is what are they going to do with it? Are they making the right decisions? We have to couch it and frame that information in a way that they make the best decisions with it. So we understand it's going to be new, and we have to work through that. All right.
This is Dave Jones with Storm Center. I was just thinking when you were saying that the public doesn't really understand probabilities anyway, and this kind of new product might be, like you said, you introduce it, and then the broadcasters, TV meteorologists will explain what it means when they see it on the air, because it's very difficult for the public to consume a probability, but seeing it graphically like this,
yes,
will probably make a big difference. And then getting the TV meteorologist to put these kind of graphics on the air, really producing a story that you can run multiple times, it really is going to be a large public effort for awareness.
Yeah, no doubt. We understand that.
Yeah, I was going to say, Brad Panovich from WCNC in Charlotte. I think a good analogy or a good product that's similar to this is the wind probability swaths from the Hurricane
Center. Yes.
To me, which are one of the best products they put out, because it really tells the story much better than a line track.
Yes, yes. So we're getting to that point. We see sort of that's the trajectory of science and technology where we're going. We need to bring that down to the severe convective side and be able to do that same sort of thing. So we have some work to do. Yes?
Cheryl Nelson with Storm Center. I'm looking at that graphic there, and what types of numbers are you considering making the pink, the red, the orange, the yellow as far as probability is concerned?
We don't know yet. In fact, we just got funding to do a major project that we are calling the probability of what, right? Because it might be climatology. A climatological number for a tornado might be 0.3%. And that can be a very high number, but the public will never get 0.3% as being a high number. So we have to have sort of our internal probabilities and know what it is against climatology, and work it downscale from the large scale, regional, what SPC puts out, all the way down to the local scale, and make sure the mathematics work all the way going downscale.
Exactly, because I think that's where it could become dangerous, because as somebody else said in here before, if somebody sees even less than 50%, they might think, oh, the tornado is just going to miss my house, I'm not going to pay attention, not go to my safe room. Then if there's that little shift, I mean, bad things can happen.
Exactly. This is why we're running it through testing before we're going to go live with any of this. But some of the signs that we've been seeing is people go, oh yeah, I understand, now that I know what you're doing with this, I understand how I might change my behavior with that, and that's what we need to know.
Thanks.
Yeah.
Hi, Craig Setzer from Miami. So, as Brad mentioned, it's similar to the
wind speed probabilities, but the Hurricane Forecast Improvement Project is doing a lot of social science work now on how the public perceives the cone, variations of the cone, onset of tropical storm force winds and things like that. So are you working with them at all, because they've made some progress ahead, and as opposed to having to start from scratch?
Yes. Yeah, we're taking everything that we've learned from other people and folding that into this as well. So the Hurricane Center's path, they've got probabilistic surge information that Jamie Rome and others have been doing, and we've been in conversation with them as well. So we're not going to try to reinvent, what others have already done. It's a good headway they've made. I think we're smarter than that. We're not going to try to, build it ourselves. Okay, so the current method on the top, this is from the May 20th, 2013 tornado event. What you see is the polygons that the Norman office issued for that tornado path. And then at the bottom, you see sort of a mock-up of what those probabilities might be. And it's a little hard to see on the images, but there are numbers. There are probabilities at all those grid points. And you see a color shading corresponding to the high value of those probabilities. And this is what we envision that end users will be able to see, that the cone is much more focused on where the tornado path is. Let's face it, when the Weather Service issues a tornado warning, they draw the polygon for the entire supercell, right? Because they got to cover the hail and the wind phenomena in there as well. So when they draw this huge polygon for a tornado, that's why we get our false alarms. But if we can just take this down to a tornado grid, that area is going to be much smaller. My hope, my hypothesis, I guess, is that society will start to calibrate itself. Because in the facets regime, they would very rarely get the red alert for a tornado. But when they did, they got hit, or it was very close to them. So the next time a red one comes up, they'd be more likely to take action based on that. Again, we have to test this before we go live with it. All right. So I'm going to move rapidly through the remaining 7 steps here. What the second facet is what the forecasters use to make decision. All the models, satellites, and all these sorts of things that we use to make our decisions, and especially looking forward towards warn on forecast types of things. We affectionately call facets as sort of the delivery mechanism for warn on forecast. Here's where it really all started for me. I was sitting in a briefing when I just got to NSSL, and I was briefing on warn on forecast. And they were showing an image just like this, where they showed the rotation potential 2 hours in advance or 30 minutes in advance, and where the track was. And my first thought was, we're going to take that high resolution, rich data set, and we're going to turn it into all capital text. That's just wrong. I'm sorry. Putting all this money into this research and turning it into all capital text is not going to be the way to go. So this is where facets really started realizing, or we started realizing that facets can be the delivery mechanism for that high resolution storm scale ensemble probabilities, and probabilistic flash and mirrors and some of the other things that I've already mentioned earlier on. And the interconnections here for us, warn on forecast certainly, what we've discovered that phased array radar actually makes warn on forecast data more reliable and more accurate, and that feeds right into this as well. So we're trying to combine all this as NSSL assisting the Weather Service in improving its warning and watch system. The third facet is the forecaster. That's the person making the decision. And I want to stress that we're not taking the forecaster out of the loop. The forecaster is over the loop and making sure that the guidance that they're receiving is telling them what needs to be done. Forecasters in and over the grids, they are essential to the warning process, and this is going to require a whole lot of training for forecasters to change. I equate this to when we went from the old 74C radar to the Doppler radar. Weather Service went through a fundamental change of how they did warning operations, bringing their forecasters in and training. We are planning for that sort of thing as well. We're going to have to train these forecasters in a new way to communicate the probabilities and threats and such. The fourth facet is the threat grid tools. And this is we're spending a lot of time with the Global Systems Division up in Boulder, Colorado. They are developing tools in AWIPS for the forecasters to use to do this. And what you see here is sort of a mock-up of a little tool that we developed at NSSL. The forecasters are actually using this in the hazardous weather test bed to develop these probability plumes. All right, so we're developing the tools for the forecasters to communicate those probabilities at grid points updated rapidly. Again, This last spring, we had forecasters in one room, emergency managers in the other room looking at the output from here, and they were really liking what they saw. And I would really like to get the broadcasters into that mix as well, and the vendors as well, to start thinking about how we create that information. The usable output is the fifth facet. What is the forecast? What is the end user going to see, and does it make any sense? Yes, there will still be legacy warnings. They will probably be a much smaller area because they're focused on where the probabilities are highest for the particular phenomenon. But they allow the end user to set their own thresholds. Schools and hospitals and such could be doing that, set their own thresholds. And this is going to blow apart the whole notion of lead time. Because the way we do lead time now is when the deterministic warning is issued, right? Between the warning and the event is the lead time. But now you give probabilities, hours in advance, and the people start taking action. Well, guess what? That's their lead time, hours in advance. It's going to be an individual thing, not a measure that we do on the inside of the Weather Service alone. All right, this will also allow us to do better impact communication, decision support kind of things. What we see on this kind of thing is GIS-based information. And so if you have a high probability of winds in excess of 60 miles an hour going through an area with a lot of trees and mobile homes, you can use GIS data extraction to give that information, put that information out there such that numerous trees and branches will fall, roofing material will be peeled back, etc. Facets is also multimedia, multi-point enabling. So if you like your all caps text, good on you, great. We can still do that if you really want that. But what we're really looking forward to is the future, different platforms, cell phones, GIS, on-camera types of things. And then down the bottom left-hand corner is the hazard simplification types of things that the Weather Service is already working on. So facets and hazard simplification do work together. So what does the end? Yes, sir.
Can you give an example? I think I get what you're saying about you're still going to have the legacy warning, but then you'll give more detailed information if you have a tornado along a certain path.
Yeah.
So what might an end user see or get or produce by themselves? I'm in the warning area, but the path is 5 miles north of me, so the probability is low. Or what? Can you give an example?
The video showed a little bit of that, and these are just initial thinking, initial thoughts on our part. But trend lines for my location, right where I'm at right now, based on geolocated cell phones, the trend line is increasing. All right, and then as the trend line crosses some threshold, the Weather Service issues a warning. So you actually get both. You can get a warning, but you can actually see the trend line before that warning is issued, and then after the warning is issued, you can see if it's still going up or it's coming down. So you get both out of this approach. Does that answer your question?
Yes, thanks.
Okay. You can have it all. All right, effective response. This is where we spend a lot of our time with the social and behavioral scientists to make sure that we're communicating this the right way. Everything I just described is along that lower panel there, the method, the guidance, the decision, the tools, and the output. Well, what really matters is, what does the end user do? What are they thinking? How do they get their information? What's their education going into this? So what we have to look at this as a holistic experience where we're taking social and behavioral sciences and the various disciplines and applying them at all the various steps of the path, the steps of the process here. And in fact, we have started bringing in social scientists, human behavior, human factors folks. We even have an anthropologist walking around in the building, and his insights are just incredible in terms of what the tribes are doing inside this warning community, right? So we're learning a lot about how we operate, and that's going to be very important as well. So I call it the facets epoxy, integrating social, behavioral, and physical sciences together. And the last facet is verification, all right? We all know what verification means. We all tend to think of it as meteorological verification, but we're pushing farther beyond that. We also want to measure the response. So we're putting in place things that measure how well did the public respond, how well did the broadcast community understand what we were saying. So we have metrics that we check in against. It's not just the meteorological verification, it's also the end user verification that we will be looking at to help refine the system and make it as effective as possible. And this also helps with our operations to research. Once we discover we got a problem, we can turn that immediately back into some research activities that help us moving forward. The beauty of going to the grids is that your forecast and your observations are going to be on the same coordinate system, finally. The way we do our verification now is just really ugly. I will say that on camera. Really ugly. But that's the way we've been doing it for many years. But by putting your grids and your forecasts on the same, your forecast and your observations on the same grid, you can start doing things like Breyer scores and looking at reliability and resolution and tell much more meaningful, get much more meaningful information about how the quality of your forecasts and your warnings. So, new metrics will be possible. So facets, my summary slides here. Facets is this integration of social behavioral sciences in all of it. And I stressed for social behavioral sciences the effective response. That's where we're going to spend a lot of time with them, but they are already working with the forecasters, sitting side by side with forecasters and helping us design the system. It is also a framework to focus the research and development activities. When I got to NSSL, I called it the primordial soup. All these research things going off, all of them different places, that there was no framework to put it together and say, here's how it can all fit together. So we worked on that. And over the horizon, we're looking at doing things with the Weather Service and aviation, tropical, winter weather. Same sort of notion. It's all probabilistic and grid-based. And some of you know about this already. In the interest of time, I'm going to wrap it up and talk about the expected benefits, continuum of weather information, reduce the size of that warned area, that red area, and get it much more refined and smaller. And we see lots of opportunities for America's weather industry value adding. You know, when you start throwing out all these probabilities and they can start doing really creative things with it, I'm really excited where they can take that. And we need to start looking at that already. And recipient-specific information, and this is all really under the umbrella of Weather Ready Nation, what we're aiming for. All right. I think that's it. All right. We can talk afterwards over beer.
Thanks very much, Lance. This is really interesting seeing all the facets work that you're doing, and I guess it's really the challenge of research to operations. Is that really the bridge that you're offering to NOAA and the National Weather Service?
Yeah, that's the great divide between research and operations, but we are working hand in hand with the Weather Service in developing it so that, as Louis Uccellini always says, there's a catcher's mitt on the other side. So what we are developing, they will be ready to implement and work on. And I think we're seeing some really great strides we've made in bridging that chasm between the research and operations.
And one of the questions that I had was, in the hazardous weather test bed, you said you opened it up now to some broadcasters that may be able to come in and observe and work with you. Mm-hmm. Are you inviting in the weather vendors as well?
Yeah, so we're getting a little bit jumping ahead to the broadcasters, but this is so new. We want to at least see what the broadcasters might do with it, right? And then we know we got to go to the vendors because they're going to have to build the things that in order for the broadcasters to use it. You know how that works, right? So we're going to sort of do it at the same time, but maybe the vendors might be a little bit later, but very close.
Any other questions in the room here? Paul?
Great talk, Mons.
Thank you.
Paul Goodlow, Weather Channel. You talked about mirrors.
Mm-hmm.
What's the timeline for actually doing testing on that?
We are testing that this spring. It's going to be our first sort of operational testing of that. And if your next question is when does it go operational, after that we got to see how it goes in the spring. You know, it's really hard to predict that. All of this, facets especially, I give sort of in the 2020 to 2022 time frame. And mirrors might come a little earlier than that. You might start seeing some of the capabilities out there.
And then the map that shows the reduction in false warnings, showing a good half of the U.S. What's the idea of what facet would do in terms of shrinking that red area?
So when we issue our tornado warnings, as I mentioned, the polygon that we draw for the tornado warning is for the entire supercell. Whereas for a tornado threat, the threat is much smaller in that area. So we will be refining. We will have a tornado grid. We will probably have a hail grid and a wind grid probabilities that complement that, but they are different grids. So the tornado area, the tornado warning area, is going to be much smaller because we're focused on the phenomenon itself, not the supercell, not the parent supercell. So my expectation, we're going to see a massive decrease in the tornado warning sizes based on going from the old way to the new way. Did I answer that okay? Kind of? All right. Now,
just a quarter of the Northeast or state, the size of Texas versus half the U.S.
Oh, well, my goal is the 30% reduction in the red area.
kind of pinging off what he said, so that map that you did, which was very eye-opening in terms of it, but what actually is really happening to get the perspective of even the people that are overwarned for any severe weather.
Yeah.
Because the tornado, as you said, the tornado warning is saying there's going to be we're expecting severe weather in this polygon.
Right.
And embedded within that, there could be a tornado. So I think to Paul's point, if you said how many people got severe weather when a tornado warning was issued, like maybe it is the size of Texas or something like that, where that verified. They got the severe weather that was associated with the actual tornado, but you're right, it's a very small area.
It's going to be much smaller. Yeah.
And we've said that for a while. We joke about it sometimes, that the concept of a severe thunderstorm watch is down here, where 30 years ago there were more severe thunderstorm watches than there were tornado watches, and they meant something. And now it seems like the forecasters are like, I gotta cover my butt here. There could be a tornado. I'm just going to issue a tornado watch.
Okay, let me. I know we're over time, but let me give one anecdote here that really exemplified this for me. It's the moment I realized we're onto something. One of our forecasters in the HWT was working a bow echo event, little comma head thing, and you're on the fence with these kind of things, tornado or not. In the old mode, she was sort of in the old mode thinking, warn or not, I don't know. The stress of that yes/no decision, and suddenly she realized, wait, this is a new paradigm. I can start raising the probabilities of a tornado out in that area without triggering the warning, and let you all know that something is happening out there that I'm interested in. Two things happened. Her stress level went down. The second thing, information was going out the door that wouldn't have otherwise gone out the door. You expand that to the watch area. All this is the same thing, just on a different scale. So you start to refine your information, continuous flow as things are changing, and the challenge is going to have you all keep up with it as it's pumping out the door. We're going to need to give you tools to do that.
That's great, Lance. Thanks very much. We really appreciate your presentation. And for those of you watching online, we're going to bring Lance back and also Phil Klutz back for questions live online. So we're going to take about 10 minutes, rearrange, bring some chairs in to set the two morning speakers up, and then we'll be right back for your questions and answers. So come back, stick around for the next 10 minutes, and we'll be right back with you. Sometimes these question and answer sessions last 5 minutes. Sometimes they last longer, 20 or 30 minutes, depending on how many people have questions. So those of you in the room, broadcasters, if you're getting any questions tweeted, that's the time to ask them as well, too. So thanks very much, and we'll see you back here in about 10 minutes.